ideas in basically differential form is a tool. It's a certain tool in differential geometry, in analysis, in differential topology, and so on. And I'm going to describe it and emphasize the key points. So first I'll tell you in general something about one forms and vectors and vector fields. Then explain you what the in general concepts are, and then well, forms. Let's see. K-forms, then the algebra of the K-forms, which is the exterior product of K-forms, and then the exterior derivative, the analysis. Well, there is one thing that I missed. There's a pullback. I need to explain that. Well, then the most important thing here is so-called Stokes theorem. So if time allows, that's what I will try to explain. Okay. So, well, let's start from one forms. And vector fields. Well, a vector field is basically a first order partial differential operator. So it is something like this. Well, and there is summation over I, of course, from 1 to n. So over repeated indices, there will always be a summation. I'm not going to do it. I'm not going to write it. So that's a vector field. It's a first order partial differential operator, but these are pretty much arbitrary functions, and there are n of them. So if you know this, they'll know that. If you know this, then you could just read off what we saw. So it's just a way to write down a vector field. Why is it nice to write it this way? Because when you change coordinates, and differential geometry is all about changing coordinates, then this thing remains the same. It's invariant. So it's an invariant definition where the components will change. So if you have a change of coordinates, well, if you want, we call it a diffeomorphism. Then, so basically our xi are functions of some other coordinates x prime. This is some notes. So these are n equations of n variable. That's a change of coordinates. So then of course the partial derivative will be transforming with this Jacobian. Right? So of course there is some of the j which I don't. Right. So that's the chain rule. And that's one of the most important things in differential geometry. Everything is based on that chain rule because you change coordinates all the time. To carve a manifold, you do different coordinate systems. So you see what happens now if you take that and substitute here, then of course that will become dx j dx dy dx j. So now these are Again, I'm not writing the sum. There is sum over I and sum over j. So this is the new x prime j. So this is equal to that. So when you change coordinate system, the component of a vector field change according to that rule. But this operator is a differential operator, stays in that. Okay? So a vector field is something where this is the rule for changing the, let me just write it. So these are little x, these are coordinates, these are the vector components. See that this is the matrix. In that book, well, you write this as xi is equal to fi of x prime, and then this matrix is what you know df. That's the matrix, right? And then you take that and you multiply this vector by this matrix. That's the Jacobian matrix. So I'm not going to use this notation maybe because it will confuse you a little bit. But that's how the vector fields change, right? So the only thing I use here is this chain rule for the partial derivative. So now if you have one form, what is a one form? Vector field is a first order linear partial differential operator acting on some function. And one form is, well, let's call it alpha. And one form is something that looks this way. And there is sum over I. My dxi, well, is a differential, so the coordinates. So this object is in some sense dual to that, but you'll see in what sense it is dual. So that's what is called one form. And if you do change the coordinates, then how does this change? Well, partial derivatives change like this, but the differential will change according to that rule. Again, there is sum over j. So here is that Jacobian matrix again. What's the difference between this and this? Well, this matrix is the inverse of that matrix. So the forms, the differential forms are transformed with the inverse of the Jacobian. If you call this df, then this will be df inverse. Okay? So in that sense, it is dual to that. So, well, if you take this, of course, you could change the coordinates here, and you'll get something like this. Alpha I, dxi, dx prime j, dx prime j. So this is a one form in new coordinate system. And you see this quantity is now the components in new coordinate system. So this is how they change. Now the vector components, this is how the covector, sometimes this is called covector, it's the same thing. Well, I call it one form because I'll later talk about K forms, and so there is no such a thing as K covector with the tensor. So that is equal to dx I by dx prime j alpha I. Again, compare these two and you'll see that this matrix is the inverse of that. You see this is dx prime by dx, and this is dx by dx prime. So these are the inverse matrices of each other. Okay? So that's one forms and vectors. Okay, so now, another thing that you should realize is that, well, I already mentioned that this is dual to that. In what sense? Well, you could define the following. You could consider the one forms as functionals of vectors. You could say, let us define alpha. This is a one form which acts on the vector x. And sometimes you would write it as this pairing. It's not an inner product. Don't call it an inner product, because inner product is for the same objects, like the inner product of two vectors. These are not two vectors. For inner product, you need a metric. I don't need a metric for that. This is a, well, sometimes called pairing. So you have one vector and one covector produce a number. And this number is obtained as follows. So it is just alpha I x I. And of course there is sum here over I. So why is this well defined? Well, it is well defined because in a different coordinate system, this number will not change. If you do it alpha prime j x prime j, then this is equal to that. Why? Because this transforms with the inverse matrix of that. And so they cancel each other and you get the identity, you get this invariance. Is that clear? Okay, so think of this as being a linear functional on a space of vectors. So we call this tangent vectors and these cotangent vectors, and then they live in the tangent space, these live in cotangent space. So these are, well, tangent space is, you know, this way the cotangent space is. But you don't need to think about that at this point. So important thing is just to realize that there is this mapping. So you could look at one form says the linear functionals on this space of vectors. Now, what is a tensor? Well, you could generalize that notion by basically taking as many vectors in some vectors and some covectors, take the tensor product and then define a tensor. So what is it? A tensor. Well, a tensor is a multilinear map on these vectors, on covectors. But I'm not going to write it in